Okay, we are live, hopefully. Hello, people. Okay, yeah, things seem to be working fine. Just in case, if the audio doesn't work, you know what to do. If the audio does work, you know what to do. So, we are gonna do a little bit more graphics programming today. Not sure how long it's gonna be. We'll see. I think I might have a little bit of a cold, so maybe we'll aim for like 2+ hours, not 3+ hours today, but we'll see. So to remind people where we left off last time, this is almost where we left off last time. So we can render the scene. I broke some stuff, I think. Let me revert. I think I tried a small thing. Let me revert this. So we can render the scene. We can render a scene with shadows, and as of last time, we can render the scene with shadows that are soft. And they're soft in a decently physically plausible fashion. It's not exactly physically plausible for a variety of reasons, but it's like better than it was before. And off stream, I did a couple small things. I added a way to toggle blurring at runtime. So this is what we had in the stream before the last one, and this is what we did on the stream on the last stream, right? I did a couple other things that I'm just gonna quickly touch on. So the one thing that I won't really talk too much on stream, but the one thing I did is I re-implemented like compaction. So when we run the code now, you can see here that when we build the initial acceleration structure, it takes like 285 megabytes. But then what you can do is you can do this compaction step that tells the driver that once you have built the acceleration structure, it can then repack it to be smaller, possibly, and in this case it's much smaller. One reason why I did this is that I upgraded AMD drivers. They got better with performance, they got a little bit better with PPH construction, and so I felt like I should fix this, but this doesn't actually impact ray tracing. The compaction doesn't impact ray tracing performance per se, at least on my GPU. It's just a nice thing to do. I don't want to stop and like talk more about this because it's like fairly straightforward. It's just a bunch of extra Vulkan code. And then the other thing I did is I added text rendering. I'm gonna probably write a small blog post about this because it's kind of cute, but we now have a shader that has a bunch of weird arrays, and it has a bunch of weird math, and it does a bunch of compute writes. But what we get out of this is you can see we have actual proper text now instead of dumping all of the text in the title bar. Dumping all of the text in the title bar has problems. One is the title bar is small. The other one is, hilariously, whenever you update the window text, when you use my specific configuration, which is like Wayland plus libdecor, which is drawing this title bar. So whenever you like update the title bar, it creates a bitmap on the CPU where it does this font rendering to bitmap on the CPU, and it takes measurable amount of time, like 5+ milliseconds per frame or something like this. I forgot. Something not insignificant. So I kind of had enough, and I wanted more text. And I thought about integrating imgui, but I decided against it for now. So we now have text. Text is cool. So what are we doing today? In general, it feels like shadows are this. How do I put this? Before ray tracing, shadows were these impossible problems that you could spend basically infinite amount of time on. I know games that had dedicated shadow rendering engineers for like 3+ years. because they worked on, like optimizations and quality improvements and soft shadows and noise reduction and transparency support and God no, like there's so much. And with ray tracing, clearly the technology has transformed, but the problem didn't. And so it feels like you can still spend an unlimited amount of time on this. But there's a couple of things I want to fix or I want to improve. And some of them are interesting because they the one thing I want to start with, and I don't know how far we'll get in general today with the stream, but the one thing I want to start with is I want to add support for transparent objects. As you can see, for example, I mean, this is a good example. The better examples are here. So if you disable blurring, you can see that the branches cast these shadows that are very precise, but the leaves don't. And the leaves could cast a shadow, but the way we integrated shadows, the scene has all sorts of weird issues with data. That's a separate problem. But so when we integrated shadows, I think initially on stream I just left the non-opaque objects casting shadows, but here I disabled this, and I can re-enable this. So the way that these are disabled right now is very simple. We just say when we cast array, we say call all non-opaque objects from the array cast. So if you just disable this, yeah, hold on, there's like a thing I have to do. Okay, so when you re-enable this, you get a lot more shadows, but they're also a lot more broken, in the sense that what you see right now is you see the geometry behind these leaves casting shadows, but the geometry is a quad, right? Or here you can see like a bunch of quads casting shadows. Whereas what you want to see is you want to see leaves casting shadows. And for that to happen, we have to somehow, when tracing the ray, when we hit a triangle, we have to ask the triangle whether the pixel that we are hitting in the texture that is assigned to the triangle is transparent or not. So this will come with a cost. Even the change that I've done just now should come at a cost. Let's undo this again and then, well, this specific change, well, right, the change that I've done just now. Anyway, there's going to be performance consequences for doing this. We are going to see what they are. They're not going to be nil. They might be somewhat significant, we'll see. So this is like one problem that I want to address. There's another problem that I don't know that I want to address today, but so now that you can toggle between shadows on and off, I was talking last time about, like ray distortions and stuff like this, but then we went ahead and implemented a white blur kernel on top of the noise that we are introducing into the image. If you look here, I'm not sure if this is hidden behind. If you look here, then when I enable blurring or disable blurring, you can see that the shadow is blurred next to the contact point. This is like wrong. This shouldn't happen. This is not how shadows work. But for us to be able to fix this, we need to know how far did the ray travel until it hit the intersection point. This is totally possible to do. It's actually fairly easy to get this value out of the ray tracing code, and then we could apply this value when we do the blurring. The problem is getting this value will increase the performance further or decrease the performance further, because we'd have to switch from the mode that we are using, which I think I talked about last time, terminate on first hit, where it doesn't matter which object we hit, we just hit whatever and we stop the traversal. And we have to disable this flag to be able to get the closest intersection, which is the default. So right now, for example, shadows take 0.65 milliseconds on this view. And then if I disable this guy, well, now they take 0.66. So on this specific view, this is like an insignificant increase. Let's look at this. So this is 1.7 and this is 1.07. So on this view, there is a substantial decrease in performance that we would incur by disabling this flag. And in general, I talked about this before, like in 4K, our total shadow cost is now 4 milliseconds or so. The blur is kind of expensive. The shadow casts are expensive. It would be nice to fix this. Unfortunately, so we can optimize the blur a little bit, which would be nice, but the shadow casts are still expensive. And the only reasonable way for us, we are casting 1 ray per pixel right now. So the only way to fix this is to cast like less than 1 ray per pixel. So I am hoping to do half resolution, half by half resolution shadow cast as well, which would hopefully still work okay from the quality perspective. We'll see. But anyway, so this is the general plan, but I don't know how far we are going to be able to do to get today, because I don't know how long I want to stream to be. So let's start by doing transparent objects, and then we will see. So again, to do transparent objects, the only real issue is we hit a ray, or we hit a triangle with a ray, and then we need from this triangle to go all the way back to the texture data. And so this is somewhat difficult in the sense that we don't intrinsically have this data. When we do shadow map rendering, for example, in the rasterization pipeline, we just have, or we can have, the UV and texture data almost for free. So for shadow maps, last time I was talking about the fact that the thing that we did with the ray jitter that kind of turns into high quality blur, high quality penumbra, and we got this almost for free. Well, except for the blur part, but it's a separate story. Unlike that thing, which is much easier to do in ray tracing than in shadow maps. In shadow maps, you get transparent objects basically for free, and in ray tracing, you have to work a lot for it. But the good thing is that because we have converted everything to bindless from the texture perspective, and even our render itself is not bindless, but it's kind of bindless in the sense that we render the entire geometry in a couple draw calls. And so all of the geometry data is on the GPU and we can access it. This should make it easy for us to try to do this. The one difficulty with all of this is that there is no debugging. RenderDoc doesn't support ray tracing yet, so we will see what happens with the code that we are writing, because if the code has bugs, then I will have to guess as to why these bugs are happening. Like, I won't have a way to actually debug this. Anyway, so first I want to just briefly talk about the API stuff. Oh, and I want to do I want to also do I want to be able to toggle the thing that we are going to write now, because it's like expensive probably, and it's nice to be able to do that. But I'm going to do that later. Maybe I'll first write the code. So once we remove the flag that says that right now we are not processing non-opaque objects. Once we remove this, then the shadows look very weird. And the reason behind this is that we kind of were not using this API fully correctly. The way the traversal loop works is this. So we call, I talked about this on the first stream, I think. You initialize the query, this just sets up some bits, and then you call proceed, which traces the ray. But when you trace rays through a scene that has both opaque and non-opaque objects, which is like an official Vulkan feature, Vulkan ray tracing feature, they have a thing called, I forget, it's like ray, Vulkan spec ray query, ray interest. They had, oh yeah, yeah, okay. So in the ray traversal chapter, I think they have this protocol for how ray tracing works. Oh yeah, this thing. And I won't, I've read this a little bit before, I roughly remember what it says, but basically it says that the ray hits an object, and if we had the mode that said opaque or non-opaque, then like the protocol is the ray just hits an opaque object and it stops there. But if the ray hits a non-opaque object, then what is supposed to happen is you're supposed to process this object somehow in the shader and then either confirm the intersection or not confirm the intersection. So, and because we are not confirming the intersection here explicitly, but then we are checking whether we actually hit an object, like the code doesn't really work. So the way the traversal is supposed to work, I think, is, well, the basic traversal should actually, wait, no, come on, this. Okay, so this is the more correct way to do the traversal code, and this should actually work with or without the no opaque, with or without that flag, right? I think it like costs a little bit of performance to do this the right way. Let's see, 1.7 versus 1. It's like it's slightly slower to do the confirm, even if it shouldn't matter, but this is just because the code I think that the compiler is generating is a little bit more complicated. But the actual thing that you're supposed to be able to do here is check the object, check the object's ID, check the triangle that you're hitting, check the barycentric coordinates that you're hitting, etc., and then perform some decision based on this. So they have these they have these like functions. So let me just write them, and I think they take like a boolean. I don't want to focus too much on the particulars of the API. So what do we need? We need to be able to get to the texture coordinate data and to the texture data from this shader. To get to the texture to get the texture data, we need the texture object. To get the texture object, we need the texture ID. Texture ID for us is inside the material, which is referenced by the mesh. There's like a bunch of indirections throughout data that I think for now, like I want to first write this code to see it working, and then I want to change the memory layout a little bit to have things hopefully be a little bit faster. But I don't really know what the performance consequences are going to be of the code that we are writing, because I've never done this before, so we'll see. I don't have an intuition for this. So instance ID is the ID of the mesh that we are rendering, and then there is the well, there's barycentrics, which is a vector 2, I believe. But the other thing that I want is the triangle ID, because the way geometry rendering works is you have like an index buffer and the vertex buffer, and when we built the BLAS, we fed all of this to the driver, but the driver disregards, or it forgets all of the index information that you had, and it just stores triangle data inside of the acceleration structures, the triangle data being positions and the index. And so the only thing you can get back is you can get back the, is it called primitive? Yeah, primitive index. So the shader still compiles. I don't know if these are correct or not, right? One thing I think we can try to do, and I did this before, so it probably works. We can do it like, we can ask, okay, for every other triangle, like don't confirm the intersection. So, okay. This appears to work correctly, yeah. So you can see that some of the triangles now cast shadows or some don't, but crucially the shadows from the opaque objects didn't change. The shadows from the transparent objects did change. For some of these objects, this almost looks like correct shadow, and if you blur it, you will not be able to tell the difference. So in some sense, what we are about to do now is almost like not as useful. Like, so here, this is actually a reasonable shadow, I guess, from this object maybe. Here, clearly, this is not how the shadow should look like. But anyway, so what happens here is if we hit an opaque object, then I think the ray proceed function just returns false because we've hit the opaque objects. We can stop there. Oh, I should check if this works with ray flag 0. Okay, it does seem to work with ray flag 0. So yes, I think this is correct. But then if we hit a transparent object, then the traversal code says, okay, proceed returns true, which is basically saying we have a candidate object, but we could either just keep going kind of through that object, or we can stop there. There's other things you can do here. For example, one thing we could do is we could, instead of just terminating the traversal when we encounter a transparent pixel, we could probably accumulate the alpha that we're hitting in the opaque objects, or in the transparent objects, sorry, and sort of just accumulate this alpha into the output shadow factor. I don't want to do this because it feels like it would just make things slower, because I'd rather terminate the traversal at the earliest opportunity. Plus, the way that we render these objects right now is with alpha testing anyway, so like there is no blend region around these, right? You can see that. So I think it's fine to just check the alpha of the pixel. But anyway, so this tells us that this filtering sort of can work. And then what we need to do is we need to get from this data to the actual pixel data in the texture. So to do that, we need a bunch of data that we don't have. But it should be very easy to just bind this data. So if I go to the, I guess the mesh shader. So let's look at what we could do. So we have the array of draw calls. This should be indexed the same way as the instances are in the ray tracing data. And then from this stuff, this has the mesh index and the material index. The material then will have the texture index. The mesh will have the level of detail data. And because we always use the first level of detail for ray tracing, we can get from that to the index offset. From that, we can get to the index buffer. I'm starting to think maybe I should just immediately, because this is an insane amount of indirection. So even to start thinking about accessing vertex data and index data, I need to go from mesh draw to mesh. I guess this is embedded, so this is not an indirection. But then I have to go from mesh draw to material, from material to texture. And then I have to bind all of these buffers. I guess that's fine. Let's just bind the data that we have for now, and then we will. This will very likely be suboptimal from the performance perspective, and then we will fix this later. So I want draw call data. I don't want meshlet data. All of that's not useful. So then I want material data. This array. Okay. Oh, and I need mesh data as well. Interesting. Why is... I guess it's like here. Yeah, okay. So, draw calls reference meshes, and also draw calls reference materials. From the material, we can get the texture index. From the mesh, we can get the vertex and index offset. Using vertex and index offset, we should be able to index the vertex buffer and the index buffer. Do we never... I guess we are never reading the index buffer in the shader right now directly. Because right now, the only reason why we even still have the index buffer is because we still support the traditional raster. But okay, that's fine. Why is this changed? Okay. So, all right, so draw calls. Oh, I was pasting them. Oh my God. All right. Hold on. Let's do this again. I was pasting in the wrong place, which is why things are not right. Okay. So, meshes, and then materials, and then we'll need texture data as well. So I guess I might as well bind, like, we'll have to bind like a ton more stuff to the shadow shader. All right, so meshes, materials. So let's see, draw calls, meshes, materials, and then vertices, and then we'll need indices. And then we will need the texture sampler. Will we? I guess we will. Yeah. And then we'll need our array of textures, which is how we should be able to actually index all of this stuff. Okay. So that's a lot more stuff. Draws, meshes, materials, vertices, indices, sampler. I think this is where we are doing all of this. So this is draw buffer. I forget if, yeah. And then we need mesh buffer, material buffer, vertex buffer, index buffer, and then texture sampler. Okay. So I think, oh, and I think these guys are gonna be automatically bound. I forget how, I already forget how this works. Hold on. Because this is not a push. Hold on. Okay, so this is the set. All right, yeah, okay, that makes more sense. So we'll need to bind the the textures, like the entire array of textures that we're using when we are doing the shadow dispatch. So like here, and it's not graphics in this case, it's compute. Okay, so I don't know if any of this code is correct. So let me enable validation layers. I've added support to just be able to like enable validation layers without like without changing the CMake configuration. All right, and then we have to enable like a bunch of extensions to be able to do all of this. Okay. All right. Right, and then I think this is saying, I'm not sure, but I think this is probably saying that the index buffer was created without, yeah. Yeah, without saying that we can, so like when we create a vertex buffer, we say it can be used as a storage buffer, but when we create an index buffer, it's just an index buffer. So again, for now, I will probably rework this, but I'm not sure if this will happen right now or not. So I want to first try to get things to run. Okay, let's see. So the descriptor is not compatible. The pipeline layout only contains one set layout, but you're attempting to bind set to indexed one. Oh, no. Huh. Is this because I'm not using this? That can't be right. Did I? Huh, that is strange. Essentially, it is saying that I can't bind the texture data because I'm binding to index 1, but it should be at index 1. Interesting. Maybe we haven't done bind list in compute stages, so maybe. Oh, I have to pass an array layout manually, right? And I didn't do this. Aha, okay. All right, that makes more sense. I should actually. Oh, there's an assertion for this, but we are running on release, so assertions are disabled. Okay, fine, whatever. So in theory, now we have this data in the shader, and we can try to just index it and see what happens. I hope to do this fairly carefully. I've talked about this before. Writing code on GPU can be dangerous. You can accidentally index stuff out of bounds. Things may crash, yada yada. But in theory, the code that we have, the binding code that we have written gives us all of the information. So let's see if this is actually true. So we did the mesh. And then from the mesh, we can get the material. Material index. Oh, it's mesh. Wait, not meshes, draws. Mesh draw. Hold on. This is the draw call. And then the draw call has the material index. So this is how we are getting the material. And this is how we will be able to sample the texture using this weird contortion. The one thing is that because we are in compute shader, we can't index. We won't like have mip maps because we don't have gradients to get the mip maps from. It's like there's a bunch of ways around this problem, but for now we are going to ignore all of this. We're going to try to just get the pixel value from the texture and then see what happens. So this is gonna allow us to sample. Let's actually maybe try to sample just in the center of the texture or something like this. So the way this should work is essentially we can just do, so like what I want, right, is I want float alpha sample material albedo texture alpha, and then if like alpha is less than 0.5 or is greater than or equal than 0.5, then we confirm the intersection. So this is the code I want. The problem is I don't have the UV coordinates yet. So let's just start by sampling the texture and see if things even work at all. Vec2, obviously. Okay, non-uniform requires this other extension. Okay, now we have a validation error. Cool. Oh, right. I think this is, we just hacked this together when we were doing this initially. Whenever we create, hold on. Don't remember where is this, but basically when we did bindless support, there was an option to kind of, you need to set the shader stages that the descriptor set or whatever is visible from. And when we did this, I just said I don't care, it's only the fragment shader, but now it needs to be reachable from the compute as well. Hold on, where even is this? Aha, somewhere here there should be the shader. This. Why is this repeated? Oh, I left a variable, but I'm not using this. Beautiful. Okay, so we will need this in the compute. I am also glad that I have left the validation code running, because this makes it less likely that we will crash something. So let's go back to our shader. So the sampling didn't completely crash the stream, which is nice. And clearly it's doing something, right? So like this UV, I think if I change this, you see the shadows changing. Oh, they're changing in a weird... Okay, I think I do need an if then. Maybe? This is odd. Hold on. No, maybe I don't. I'm fuzzy on whether like I need to guard against opaque objects or not. Okay, whatever. Doesn't really matter. So now we need to get the UV coordinate. So to get the UV coordinate, we need to first get the vertex data, right? So we have the triangle ID. So now I need to be kind of careful. So the draw call has the mesh index, so we can extract the mesh. Draw mesh index. But then the mesh, also, hold on, before we go too far. So it is possible to have objects without textures. And if they are ever tagged as like transparent, then this code will hit them. You probably shouldn't index textures that you're not planning to index. So let's do this. Okay, so we have the mesh. Now the mesh has vertex offset, which we will need to access our vertex data. A vertex offset. And then the mesh has the index offset, which depends on which LOD you're using, but we're always using LOD 0 in ray tracing data, so theoretically this should just be index offset. Once you have this, in theory, you should just be able to read index data. So this is like indices. Yeah, this should be correct. So this should read index buffer for our triangle that we have just hit. Assuming this indexing is the same indexing that our index buffer uses, which I hope is true, because if it's not, things are not gonna be, things are not gonna work. And then in theory, we can just read the vertex data. And then I think I'm getting shader compilation errors. Let's see. Oh, you can't copy the vertex data to a local variable because of ridiculous issues with how short integer types work in GLSL. Okay, it doesn't really matter. What does matter is, given the vertex, we can read the texture coordinates. So let's just do that. And let's just read them. Let's just read them like this. So this is going to be TU, and then this is TV, and then this is so this should compile, hopefully. Okay. Now, given the texture coordinates, we should get the one texture coordinate that we need to sample from. What we do have is we have barycentrics. So I think barycentrics that are returned from this function should correspond to the order of indices in a triangle that we fed to the original blast builder. So in theory, what should happen is not this. I mean, we can go with this, but I don't think this is right. Let's see. Yeah. So, I mean, this looks sus. So I think the X barycentric is for the first vertex. So I think it should be like this. And then the third component is like barycentric coordinates define the coordinate space in the triangle where you have three numbers, but the sum of these three numbers is always 1. And then if one of them is 1 and two others are 0, this corresponds to the specific corner of the triangle. So I think this is probably the correct way. But also both look wrong. All right, so this is the thing that I was worried about, because now we have bugs in our code. And now I don't know. Let's see if this was actually right. But it doesn't, neither of these, well, This actually looks more correct. So maybe I can already be replaced by the AI. Let me look at the docs for this, because I'm like confused a little bit. I thought, surely, that this is not how things work. Okay. 2-component floating point barycentric coordinates of the current intersection. That is beautiful documentation. It immediately answers all my questions. All right. Oh, the B and C barycentric coordinates. Oh, so the A needs to be reconstructed. Oh, that's weird. Okay, okay, that's fine. All right, so then the AI is correct. So this is interesting. So this looks correct to me. Like, right? This is how I would imagine leaves shadows look. This stuff looks all sorts of weird. No? Maybe? I'm not sure. The thing is, like, this is kind of the camera perspective, so this is where the shadows are being cast from. This looks sketch, but maybe this is because of the odd angle at which the sun is being placed here. This is definitely, let me go there actually. Okay, all right, this looks broadly correct. This also looks weird, right? Like, why is there a leaf that like terminates here and then doesn't? So I worry that we actually have a bug, and it's just that within an individual triangle we are sampling things correctly, but then we have some bug somewhere else that's actually breaking this. So like it's possible that if this is one quad, then maybe things are fine. But if on the border between two triangles things are broken because some code here is actually incorrect. Because this looks suspicious. It's like both right and not right, if that makes sense. Like this part looks good, but then the way it connects looks bad. Okay. Oh, am I missing? Are we doing like 1 minus V or something stupid like this in the vertex shader? I would think. No, we don't. Yeah, I would think this would be done offline. Okay. I basically need to check all of this math because I am. It looks suspicious. It kind of looks correct, but also kind of doesn't. The self shadows. Well. Also, you can see that our decal now casts shadows onto like an object that's placed on, which is hilarious. There's a depth offset, there's like an offset, it's not a depth offset, it's a geometry offset in the scene between the decal and what it's placed on. So I guess now we have shadows here, which is cool. Not what I wanted, but cool. Yeah, I don't know if this code is correct. I feel like there is a bug. I don't quite know. Oh, you know what? Maybe never mind. This geometry is just broken, right? Like, leaves don't work like this. Leaves don't grow out of nowhere. And so whatever issues I was seeing from the disconnected geometry here, these are probably just how vegetation was created here. Like, this geometry probably just doesn't make sense. Okay, so maybe we are actually as close to the correct rendering as we can. The good news is once you blur the shadows, you can't see any of these minor imperfections. Okay, this was easier than I thought it would be. Now, the thing I want to know is how much does it affect performance? To know this, I want to add a thing that I want to have this anyway in the shader, which toggles this, which allows me to toggle this on and off whenever I want with a hotkey. So we are just gonna put a specialization constant here. And I don't want to endlessly, there's like other stuff that I want. For example, I want this hit distance that is more precise. So I just want to have the high quality and the low quality mode for now for shadows. So we'll just have a bool called quality. And then if quality is set, then we'll keep the raycast flags that we kind of need for all of this processing to work. And if quality is false, it's kind of weird to, it's fine, whatever. It could be an integer, it doesn't matter. Actually, let's just make it an integer. It's just weird to have like quality be a boolean. So if quality is 0, then we will not support transparent objects, otherwise we will. So this means all of this code we don't need if quality is 0. I guess let's do it like this. Maybe it's a little bit weird, but maybe this is fine for now, because we don't need any of this code to run, and ideally the shader compiler should be able to prune this entire branch when we select like the correct shader variant. So now if we just launch with this and then fix the bugs, this should be question mark. So this will just disable these shadows, presumably. Yeah. And then we will change our C++ code. All right. So when we create the pipelines, instead of creating just one, we'll create 2 for low quality and high quality. Okay, so when we render now, we'll just select the right pipeline. And then when we select the low quality pipeline, we technically can avoid binding like all of this stuff, but there's not really any harm. Oh, we sort of have to bind this because we use specialization constants. Never mind. Yeah, so this code basically then just doesn't change much. This just says shadow quality, wait, shadow quality 0, shadow low quality, shadow high quality, and then we'll bind if we have remaining keys. Do we have remaining keys? Yeah, we have the key Q, which is perfect because Q stands for quality. At some point I will rework this to actually be a GUI, and I have a plan to do this without introducing like GUI libraries. But for now we will keep things simple and just press buttons. And then I want to display the status of all of this in the GUI as well, in the text GUI. So shading, shadow blur, and then shadow quality. I guess this can just be shadow quality. Okay. So I think this is enough to toggle all of this at runtime, and now we will know how much it costs, right? Well, this is clearly not enough. Hold on. I think my traversal code must be bugged. Huh. Oh, oops. It's vice versa. It's like this. Okay. I think this should work now. Okay. So the good news is this code works. And the good news is the scene looks much more correct, but also better, I would say, with this, right? We have correct shadows here. We have much better definition of this tree in the distance even, right? Even though it's far away. This stuff is like correct, hopefully, etc. The bad news is this does have a significant performance cost. So if you look here, I have the timer for the shadow blur, but the blur is constant because it's just a constant grid. And then we have the timer for shadows. So right now the timer for shadows is 3.9. If I disable it, it's like 2.7. So this is about a 50% cost to our shadow rays, about 50% increase in cost to our shadow rays. Okay, and the other thing that I will note is this was very easy, almost surprisingly so. But the reason why this was very easy is because we've done all of this work before to make sure that we can have textures available at any index in the shader, to make sure that all of the data is packed on the GPU and everything can be cross-indexed so that you don't have to like you don't have to worry about kind of how I'm getting access to this data. You just have this data. It's not a big deal. So performance is a problem. There's two reasons why performance suffers in this case. So one is, there's like more than two. There's a lot of reasons. So one is we just need to do more work. To quantify the effect of the more work that we need to do, we can like disable all of this code and then just keep alpha at 0. Okay, and this is 296. Okay, so we do pay a little bit more cost for these ray flag business, right? You can actually just see it here. So we go from 2.7 to 3.0. So it's like about a 10% cost for just switching to ray flags. But then we pay all of the rest of the cost. Which is like 0.9 milliseconds, which is very substantial for sampling the textures. This is, well, there's two places where this cost could come from. One is sampling the textures. The other one is the shader is just larger, and so it needs more registers, and that has a cost as well. Okay. So I think what we will do, the nice thing though is shadows like this are hard to get with shadow maps because of the resolution requirements. Now shadows like this are not that hard to get with shadow maps. So anyway, okay, so I'm basically trying to figure out how do I want to tackle the performance issues. Because there's two things we can do about this shadow cost, and there's also some stuff we can do about the shadow blur cost. Let me commit this code, because this code, even though there is not much of this code, oh, I also changed the clear color to not be like the weird magenta that it was coming as. So let me commit this code, because this was easy, but this was also good. And then we can spend the rest of the time doing optimizations. And let me disable the validation code, actually. Validation shouldn't inflate GPU timings. It does inflate CPU timings. But all of the timings that we are worried about right now are GPU timings. Okay. Which day is this? 27, I guess. Initial implementation of transparent shadows. We can now trace through non-opaque objects. Which requires using like triangle indices and barycentrics to compute the actual alpha value when casting shadow rays. One thing we can check. So there was this thing that I was just talking about, right? In theory, you don't have to terminate the ray. You can keep tracing and just accumulate the shadow value. This shouldn't matter from the quality perspective after the blur, I would think, but let's, in our specific scenario at least, but let's actually just check that it works. I'm just curious. So how do we do that? I guess what we can do is we can keep alpha what we can do is, I guess, this. We can keep a value that starts as 1, and then instead of confirming that we have hit an object, we can pretend that we didn't hit an object at all. And then we can multiply this by 1 minus. Let's just accumulate it like this, and then do like this, and then reload the shader. Well, this is clearly not right. So if the alpha is 1, the object is fully opaque. Okay, so this is, oh, but then, man, everything is like in this weird inverse space. So interestingly, this looks exactly like it used to. Oh, that's because, okay, this code is all sorts of wrong. Hold on. This is how it should be. And then, no. Wait, hold on. If we hit nothing, no, this was correct. This was correct. If we hit nothing, this means we didn't hit any opaque objects because we are no longer confirming the hits for the non-opaque objects. And so the shadow, instead of just 1, which is no shadow at all, yeah, this should be correct. The one I'm surprised because I expected like, oh no, okay. If you look really closely, there's like a little bit of a gradient in individual pixels based on how. Okay, so this is kind of useless in this specific scenario. We can just abort the ray if the ray hit like a pixel that's sufficiently opaque. It can be useful in some other scenarios. For example, these windows that you don't see here, but there's like windows here in theory. And they have a material on them with transmittance in GLTF data. And so in theory, if we propagated all of this, fit this into this pipeline, we could like have, I guess, these pixels. If sun goes like sort of from, also ignore the flickering. I'll look at this in some other point. If the sun goes like from here down through these windows, then in theory we could cast like a half shadow from these windows based on the transmittance. This again is something that's like hard to do with shadow maps because you have to do tricks, you have to spend extra memory, etc., but should be easier to do with ray tracing. But all of this seems kind of irrelevant right now because to get quality shadows from all of this, we kind of just need to blur. Okay, so let's kill this stuff then. All right. Okay. So I guess the first thing I want to do is I want to minimize the overhead of this code. And the problem with this code is it does a lot of memory indirections. It has, so this is memory access. The longest chain goes like this. You fetch the draw. After you fetch the draw, you fetch the mesh index. After you fetch the mesh index, you fetch the offsets. After you fetch the offsets, you fetch indices. After you fetch indices, you fetch vertices. So it's like a long chain through the memory hierarchy, where every draw, every like step takes a bunch of cycles, and I'm sure this cannot be fast. So to fix that, what I'm thinking of is I want to have another copy of this data. Basically, I want to have some ray tracing specific. Maybe for now, just draw call and mesh. Will this break with level of detail? Level of detail will make things a little bit complicated. Let me think about this for a second. I want to like do something to improve this, but I don't want to complicate future work in this area too much. And I did have a plan to basically feed level of detail meshes. I guess this won't break that because I can incorporate this. I'll need to do level of detail selection on the GPU, but then I can just patch that data. You know what, let's try this and see what happens. It's possible that these memory indirections aren't even a source of significant slowdown, who knows? The only way to know, the best way to know, I should say, is to try this. So let's just note the timing. So in 4K, from the default camera perspective, we are now spending 4.12 milliseconds to cast shadows. Once we do half resolution shadows, which is definitely becoming very necessary, this should drop down to like around 1 millisecond, right? 1.5 maybe. So that's going to be way better. But half resolution shadows may come with quality issues that will take time to resolve. So I want to first sort of minimize the cost without half resolution and then do half resolution. Anyway, so just as an experiment, I guess, let's just add data. What's the best way to try this? Okay, so I think let's do this like this. Oof. This is a little painful because there's too many things to keep track of, in a sense of future development of this code. Like this data is kind of useless, except that it's useful for ray tracing. We could remove this and then add some ray tracing specific data. A lot of this is hard to balance correctly. So let's just very, very quickly prototype something. So I want to have like a vector of yeah, I can do this outside. Let me prototype this very quickly here. Maybe this is a bad idea, and maybe I should be spending time on half resolution right now and then think about this for the future. But maybe not. I'm not sure. There's a couple of different ways to do this. So, okay. Here's what I have in mind. Here's what I want to try. So I want to have these two new data structures, mesh draw and triangle, that are only for ray tracing. In mesh draw, I want to keep for now the texture index and the offset into this buffer. And then here for every triangle, I just want to keep three texture coordinates for every vertex, but then there's 2 coordinates for every vertex, 2 scalars for every vertex. So it's 6 numbers in total. 6 numbers is 12 bytes in like half precision. And I'll probably need more per triangle information in the future, like a normal. So I guess I'm just gonna bump it to 16 bytes. Because that then makes the axis patterns like easier to think about and stuff like this. So let's try this. Let's see what happens. So this will work as follows. There's gonna be, I guess we use even 16 or something like this to represent shorts. So we are gonna have 3 U1, U2. 3 U coordinates for textures, 3 V coordinates for textures. So this is 12 bytes, and then we'll have 32 bits of stuff for the future. A normal would go well here. So maybe, well, I don't know that I would want to face normal though. Yeah, this might not be super future-proof because of the size constraints and stuff like this. But one interesting thing to note is we are currently using 32-bit indices, and so even the index information for us is 12 bytes per triangle. We haven't cared enough to fix this because this path is kind of dead. It's only used for traditional raster node ray tracing. But this means that this kind of substitution of index data for vertex triangle data for this specific use case is actually not increasing the amount of data that you need to fetch, except for this padding, which we could do without this padding if we wanted to, but it's fine for now. Yeah, and then we will do mesh draw RT struct, which again, I guess is going to be 16 bytes because everything is 16 byte aligned. But the only things we need here are triangle offset into this large buffer and the texture index. And then again, padding for feature. We technically don't need to pad on the CPU side because of the alignment, but it's like, why not do this, I guess. So then let's mirror this to the GPU, and these are uints. So then these are floats 16T, and this is uint. And then instead of all of these buffers that we have just bounced, instead of 1, 2, 3, 4, 5 buffers, we will just bind the 2 buffers. One will have ray tracing specific decal information, and then the other will have the other stuff. Maybe for now, let me bind them in addition to the stuff that we already have, so that we can toggle between this and compare performance. So, draws our team. And then triangles. And then the tricky part, of course, not tricky, but the code that we have to write is we have to fill this information. Oh, and I can't even, oh, this is so painful. These indices don't point into the vertex buffer. There is an offset, and the offset only comes from the meshes. So I have to like index the meshes to be able to do this. Oh, I'm already regretting this. This is awesome. Man. The faster way to do this, or the easier way to do this, I guess, would be to go from, would be like to keep the ray tracing specific draw calls, but to ditch this stuff. You know what? Whatever. Let's just do the right thing. It doesn't matter. We will figure it out. So yeah, there is like the same problem with LODs in all of these schemes effectively. I am regretting this. It's just painful to write this code. It might be a good idea. It's just painful to write this code. Okay. Is there an easier way to do this? I don't think there is an easy way to do this. Okay, you know what? It's fine. So we'll allocate this for the worst case. This is gonna assume we will support this for level of detail, which is not mandatory technically, but why not? And then, but for now we're only, I guess, gonna fill this for the first level of detail. So we need to iterate over all triangles, iterating over all indices is sufficient. So LODs 0 index count. And then we will place the same, so the triangle that corresponds to this is going to be, well, yeah, is going to be indexed the same way as the triangles are indexed in the pack data. This probably is not making any sense to people who are watching this, because it requires remembering how things are like laid out in memory and packed and stuff, and even I barely remember this at this point. Index offset might even not be divisible by 3 if we pad it somehow. That's gonna be hilarious if we do. Oh boy. Let's see. We don't seem to pad it. Okay. So this code does not fill me with joy, but I kind of want to just finish this code just to see what the performance impact is. If the performance impact is null or nil or whatever, then I'm just going to revert this because this is bad code. All right, let's see. So the first load, the index offset plus j plus 0, and then the real, this is the same math that I was just writing in the shader code actually. And then we just need to copy the u coordinates and the v coordinates into our triangle structure. I guess it's not that bad. So these are the triangles. And then the offsets into this data come from just this guy, because this data is laid out the same way. So in theory, I guess we can just go over the decals structures. And just fill the albedo texture index using the material index. Okay. And then the draws RT. The triangle offset should be just the index offset. Over 3. All right, I think this is correct. This is probably fine. I don't know, but it's probably fine. So then we will need to upload all of this data to the GPU, and then we'll need to bind all of this data to the shader, and then we'll need to switch to using this data, and then we'll need to see if the performance is better or not. And also we crash when we actually run this code, so that's cool. I'm not quite sure why we crash. Maybe we are just hitting validation issues that maybe we don't crash in this code. Let's see. Well, that is disturbing because we do not crash in debug. All right. Okay. Is what I'm doing a good idea? Clearly no. Should I still finish what I'm doing? Probably. So the what's it called? The mesh RT, the draw RT buffer, and then the triangle RT buffer. We are going to create them. So the draw RT needs the draw call count times size of draw RT, and then the other thing just needs triangles RT size times size of triangle RT. So they're both only going to be used as storage, and we need transfer to actually upload to them, so this is correct. And then we will upload them. Let's draw RT buffer, draws RT, draws RT, mesh draw RT. Okay, that is correct. And then I need to like destroy them, I guess. Which I guess I can do. Okay, and then I need to bind them when we render with our beautiful, beautiful, beautiful code. Did I allocate? Yeah, okay, so they just go after draw RT buffer and then TRT buffer. Okay. This was a little confusing. So I still don't know why we got a crash and release, and this is a little concerning because we don't get a crash right now. And so I'm wondering if this data is just completely garbage and we will crash the GPU right now. But let's just see what happens. I can play it a little safe. So I can, for example, get a draw RT, and then this guy should contain the same offset. Is it the triangle offset? How did I do this? Hold on. Okay, yeah, I divided it by 3. Ideally, I should also check that it's actually divisible by 3. Let me do that. So what I can do is I can just compare the offset that's here, for example, or the index of the texture with the index of the texture that's here. And if they are different, then do something. I'm not sure what I should do. Like not count the ray hit, for example. So I will only count the ray hit if the data in this is like coherent, so it's the same. Okay, so that buffer is probably correctly filled. So then maybe things are correctly filled. Let's just YOLO this. So we'll have this one branch that says, oh, we are fetching all of the data from the original from the same buffers that the rasterization pipeline uses. Rasterization pipeline. And then we will have another code path. So this will be the same, mostly it should be unit, I guess. Okay. And then the other path that we'll have is the path where we do all of the exact same things, but much quicker, hopefully. So we have the triangle offset, we have the triangle ID. Yeah, and then we just fetch the triangle. I think this is correct. And then we just sort of decompress half precision values. And then we'll need the texture. I guess that's it. If the stream crashes, then our data was wrong. Let's see. The stream didn't crash. Oh, but we haven't switched. All right, our shaders failed to compile. Wait, what? Oh, float 16. Oh, we have the same stupid problem, which is we can't actually copy this data on the stack because it's of floating point type. Okay. So the good news is the code works. The bad news is the code is exactly the same performance. Let's see if that holds true on this. Yeah, we have gained zero performance back for all of this trouble. This is not slower at all. Okay. So 453 milliseconds, 450. Okay, we did gain 0.03 milliseconds by writing this code. So this means this code is effectively useless. Okay. Interesting. So experimentally, we have proven that all of the indirections that we pay for here, they're not like that bad. They still feel bad, but the code that I have just written also feels bad. And there's going to be problems with the level of detail, etc. So I think the smart thing to do right now is to leave a to-do comment saying, it might be worth repacking some of this data for RT to reduce indirections. However, attempting to do this gained us 0 performance back, so maybe not. The one other thing that could be a source of the problems with performance is the inefficient access to the texture data itself. And then if it's neither of these, then it's not even memory, it's like some third thing. So by the way, normally what you can do is you can get an answer to some of these questions without writing code to validate these by using your graphics profiler of choice. The problem is the graphics profiler of choice doesn't work, because or it works with RADV, but RADV has a different ray tracing implementation that's slower, so I don't want to benchmark that. And then on the official driver on Linux, it crashes the GPU, and it did crash our stream actually a couple weeks ago, so I don't want to do this. Okay, so like the other problem that might happen here is the access to the texture is just inefficient. This is the thing I was talking about just now, where I said, or like 30 minutes ago, where I said, you don't get automatic MIP mapping. Like, this data comes from the first MIP level of the texture. In fact, I kind of almost expected like an error here, but I guess that didn't happen. Effectively the code, is the load like a separate? Yeah, okay. Effectively, the behavior of the code is exactly identical to what would happen if I specified 0 MIP or MIP 0. So let's look again, 1.78, and then if I do this should be exactly the same. Yeah. So what you can do though is you can sample from a different lot, like you can sample from lot 3 or whatever. And that gains a tiny bit of performance back, like a tiny bit. If you look at, this is probably still good to do, because like a one-line change that slightly improves the performance is worth it. I just didn't want to do like complicated changes. So let's see what happens when you do this. So this is the level 0, right? And then in theory, we could go like level 5 or something like this. So this reduces or like increases the number of the MIP level that we sample from, which reduces its size, which kind of reduces the definition of the shadow quality. Ideally, you would optimally compute this value. For example, in this case, right, like you want something higher resolution, and you could compute this adaptively based on the pixel that you're sampling and some other things. This is a difficult problem apparently. There's a thing called ray differentials that I looked a little bit into, but not too much. So as usual, I don't want to do the right thing. I just want to do the quick thing that helps me a little bit performance-wise. But I'm not sure what that would be. So I guess... And the other thing is, like I was saying this before, right? So when you blur, like yes, you can see a difference between these two when I switch, but I doubt that I would, when shown this picture, you would be like, oh, this picture looks off. I bet your MIP level offset is like wrong, right? Like that's probably not what you would tell me. So, but the performance impact is also very minimal. So that's unfortunate. Yeah, like, so here we save like 0.02 milliseconds or whatever. So let me actually keep it at 0 because we don't gain performance this way. But this is just something to keep in mind for the future. Okay, so on one hand, we just wrote code that had absolutely 0 improvement for our performance, and so that's a failure. On the other hand, the thing I wanted to do after this, but this fails, so I guess instead of this, is doing shadows in half resolution. And so I guess we have to do this regardless. Let me look in chat to see if people have insightful comments. People don't have insightful comments. Yeah. So the nice thing about what we have just done is that if we need more data from the vertex, we could have it. The less nice thing is that there is not a lot of possibilities until you do full path tracing. So what we could do in the future is we do, I don't know, reflections. And then when you do reflections, you want to do path tracing. So you take the pixel that you hit, you query the vertex properties, you query the texture properties, you reconstruct the color, which you can do with kind of this code. But then you want to do a shadow casting ray. So then, well, the shadow casting ray is easy. Maybe you want to do a second bounce of reflections or something crazy like this. So then you need a normal, and of course you have the normal in the vertex data. So the nice thing about this code is it's very generic. It generically gives you the information that is as much data as you can possibly have about your geometry. The not nice thing is it seems like it should be slow, but I guess it's not actually slower than whatever else is happening. I don't fully understand. Oh, there might be one reason why things might be slower is just because the ray traversal takes longer because we do more steps. Because there could be situations when you hit an object and then you traverse, then you like sample the pixel and you discard the intersection, and then you're like, I guess I need to look further. And that alone could be a contributor to the performance issues. There is an easy way to validate to what extent this is a problem. What you could do, so right now it's like 1.4 milliseconds. So what you could do is you could just change this code like this. And now it's 1.12. Yeah, so that's a significant problem then. So just, because what I just did, this change I just did, it doesn't change the compiled code. The compiler is not smart enough to like know that the alpha is between 0 and 1. There's no way for it to know this because it doesn't know the format of the texture. So the compiler compiles the exact same code with like a small difference, which is the sign of the constant. The runtime behavior of this code is that when we trace array, previously there would be cases where we would hit a pixel, say, oh, the alpha is 0.1, we need to trace further. But now we still do redundant work for the first kind of layer, right? But then we trace forward regardless. And so that's a good way to validate. That's a good way to validate if like, if there's other factors that affect performance. But I guess so here, at least a significant, this is still not as fast as the code was without this, but it's like closer. So I guess the significant cost is just having to traverse some rays further because you have to traverse them through transparent objects. One other way to deal with these is to, one other way we can try that I'm tempted to actually try, because maybe it's going to be a decent idea, I'm not sure, is, but I suspect it's not, is, so what we have done is we have traced one ray. This ray traces through either opaque or non-opaque objects, and then based on which one we hit, we change the behavior of the code. The thing is, if the pixel is in shadow of the building, but also simultaneously in the shadow of a bush, it's cheaper potentially to not do any of the transparent stuff at all, because you know it hit the building. So the alternative approach to dealing with this is that we can trace one ray that is only going through opaque geometry, and then if the ray hit nothing at all, then we know we are not in shadow, probably, but we might be still in shadow of an opaque, of a transparent object. So we trace a second ray with all of this more complicated machinery, right? And so in theory, this could be faster. My gut says it's not. There could be reasons for why it could be faster. My gut says it's going to be worse. But let's try this just to close off this topic. And then we'll do half resolution. So, the way you try this, it's hard to keep both code paths around. So let me just note full resolution timer. Full resolution timer on unmodified code is 4.42 milliseconds for just the tracing with all of this crazy stuff, and then 299, so 3 milliseconds just opaque. So then the way to do this is we have two ray flags. We have ray flags, and then we have ray flags for transparency. The opaque cast is the same as what we did before, where we only trace non-opaque objects. And then the transparent cast is the reverse. We are only gonna trace opaque objects. Oh, non-opaque objects, whatever. You get what I mean. So then we have the first ray that we do, which is the old code that we had where we just call ray proceed, and that's it. This tells us, are we in shadow? So we can indicate this. Now, if we are not in shadow, so if shadow is like 1 basically, which means we're not in shadow, then what we do is we do this second, more complicated trace. I guess we can probably reuse the ray query. I'm not sure. I hope we can. And then we don't need this quality thing, or in fact the quality thing goes here basically. And then we reinitialize the shadow value using the same logic. So this is the alternative way to do this, which doesn't seem to compile, I guess, for whatever reason. Oh, wait, it does compile. Wait, did it compile? The behavior didn't change. Oh, that is better. That is much better. On this view, we went from 4.something, 4.4 to 3.8. Okay. Okay, I guess we are doing things this way then. So then this is faster. That is cool. Interesting. It sort of makes sense as to why this is the case, but I kind of also expected that maybe things wouldn't be the case. it depends on the BVH construction. And I guess I kind of expected. Yeah. For what I'm saying, there's a mechanism in the GPU that we talked about, I think last time. Yeah. Where it can sort the ray hits. And I guess there is no mechanism to sort the ray hits according to the flags in the BVH node. What could happen in theory, and this is an interesting thing where it might be worth it to keep both modes around to be able to experiment with this on other hardware. Let me think about how to do this best, because it's possible that on some hardware, a single ray is faster, because there is a way to, in theory, to sort the hits that you're getting through a single BVH trace based on their flags first. And so you say, oh, this node has opaque objects, but this node doesn't, and so you sort the node with opaque objects like before to hope to get the first ray faster. But it's interesting that in this case, this reasoning doesn't apply and things are faster this way. Let me think about how do I, in a maximally clean fashion, how do I keep both modes around? I guess I can just put them in a different... This code is almost the same as what we used to have. It's just that it needs a flag, like a ray flag thing that is different. And it will otherwise work for opaque objects. So I think what I want is I want to have two functions then. Let's actually start using this beautiful abstraction mechanism called functions. I want two functions. One will just trace opaque. And then one will trace whatever. I guess one will just trace array. The other thing I kind of wanted to do... Yeah, that's fine. Yeah, okay. So let me just extract this to a couple functions then. Because then on different hardware we'll be able to quickly try in the future, maybe if we have different hardware, we'll be able to try these different kind of ways to do this, and then maybe a different approach is faster on different hardware. So let's do a function called shadow trace. And then that's going to be position, TLS is a global direction. And now we'll just return a Boolean. But then we'll parameterize this by ray flags. And then this will return this. It's probably more logical for raycast to return like whether they hit something instead of whether they didn't hit anything. So I guess, come on. So this is going to be our our shadow trace, and then we'll have a shadow trace. Let's call it transparent or something like this. But the thing is, it will work even for non-transparent objects. It'll just depend on the flags that you put in. And so then our current logic that we experimentally established to be faster goes like this. Do a shadow trace for only non-opaque objects. And then And then if we didn't hit anything, repeat the shadow trace, but the transparent version. And also, if quality is not 0, right, then repeat the shadow trace, its transparent version, but only traverse the opaque or the transparent objects. So they keep flipping between like opaque, non-opaque. And then our shadow is shadow hit 0, 1. So this is kind of the code. Okay, this is less bad. This is less, the performance cost, I guess, is less than what I was worried it could be with this optimization. So let's check that it works. Well, it doesn't because it's now for 80 milliseconds. What? Huh. Hold on. Interesting. Even this is slower. This was 3 milliseconds. Interesting. That is unfortunate. Let me revert all of this. So this is the fast code that we had. Wait. What the heck? So the shade reloading does work. Isn't this the code that we... Okay. Maybe I just misremembered the numbers. Oh no, but then my undo history lost the function. Oh my god. All right. Let's just freaking do this again. This is incredibly annoying. Okay. I was confused because maybe I just remembered the numbers wrong. Let me do this again, and then I will just like stash things. I was just worried that some compiler optimizations are missing or something, but then my changes got lost. Ah, okay. Today is a bad day, clearly. I'm so confused because I thought I remembered some numbers, but then the numbers changed on me. Okay, so one more time. So logically speaking, this is the code we had. We do shadow trace, and then our ray flags are not listed here. Okay, so they are this. And then if we didn't hit anything, and we are operating in high quality mode, then we do shadow trace transparent, call opaque, this, remove all of this stuff. transparent. Okay. So let's do let's do the performance measurements again. So this in quality without like the extended shadow casting mode runs 392, with it runs 480, and then the code we had initially, the code that we started from, I should say, it went like this. If in quality 0 we only did the like the opaque trace, but in quality 1 we effectively did the transparent trace, but instead of only doing this for transparent objects, we did it for all objects. So okay, I'm confused because it's almost like my entire GPU downclocked or something like this in the last like 20 minutes, because all of the ray tracing numbers for some reason are different now. But the comparative performance remains correct. So 575 milliseconds with 1 trace, and then 480 with 2 traces from this camera view. All right, I don't really know what to make of the, I thought the absolute numbers were slightly different, but okay. So on MDVLK plus RDNA3, 2 shadow traces are faster in practice than 1. This may be different on other vendors or drivers. We could check performance on RADV. VK driver files to see the performance on RADV will be worse based on how it usually is. Yeah, so see now the ray tracing takes with RADV, it's like a different driver, it's like 8.4 milliseconds. But out of curiosity, let's see on RADV what happens if amazing. So on RADV, 2 traces are expensive, like 8 milliseconds. And 1 trace is much faster, 5.15. On AMD-VLK, it's the other way around. 1 trace is, 2 traces are faster, and then 1 trace is slower. Okay. Cute. And I have the branch. Oh, I don't have the branch. Okay, this is maybe fine. RADV is still missing an optimization that uses these masks for culling more efficiently. I thought I have the code compiled with that patch, but I don't think I do actually. So maybe this is fine. For example, for now on RADV plus RDNA3, 1 trace is faster, but RADV is missing pointer flags optimizations. The way RADV traversal works right now is, unfortunately, it only applies these culling flags at the very last possible opportunity when the triangle traversal is performed, instead of doing this at the first possible opportunity, which is where the object traversal is performed. But there's an open PR on Mesa that fixes this, at least for RDNA3, and hopefully that makes things better. But we'll keep both variants around, because now that it's just a function call, it's easy, and maybe we'll switch back and forth in the future as well. We'll see. Okay. And the other thing, the one thing I want to just double check is that the weird performance thing I'm seeing is not because of some code change that I've made that I will never be able to find again. It totally is. Hold on. This is just weird. I am dumbfounded. I think something is going on with the compiler actually, maybe. Oh no, okay, never mind. For 412, same thing. Okay, never mind, all good. Okay, all good. The performance gain is not that severe, I guess, then. It's like 412 to 3 point. It's like, what, 10%? Around 10% gain. But we will take any extra performance that we can get. Okay. Optimize shadow traversal a little by casting 2 rays. This relies on efficient... The weird sounds that you guys are probably hearing are the rain. It's been very rainy and cold in San Francisco over the last few days. And the unique construction of my house means that in this room, particularly these sounds are very pronounced. But that's kind of cool. I like it. You get free ambience of rain in the city, I suppose. Okay, on efficient like object filtering based on non-opaque flags in RT implementations. For example, currently on RADV, 2 traces are basically like 2x, well, like much slower than 1, as it performs this filtering too late. But like I hope, as I said before a couple times, RADV performance is not competitive right now on ray tracing specifically on RDNA 3. Maybe it is on 2, but it's not on 3. So I'm just waiting for them to improve. And when they improve sufficiently, then I think it would make sense to optimize more carefully with RADV in mind. But for now, for official driver, this is faster. Okay. All right. This is a Roblox question. Roblox questions are not going to be answered. I don't even work at Roblox. Unconditionally shoot 2 but change max distance. I can try this. I assume it's the same. I think you probably are saying, hey, is the branch costing us much? I would guess it's not, but I don't know. We can try. That's an interesting suggestion. So let's do that. Let's run the code again. Branches are not free, but the thing that shadow trace is hiding right now, the thing that, even if you ignore this code that seems scary and large, what this code is hiding is like a loop with branches, with memory accesses, etc. So I wouldn't sweat an extra branch is what I'm saying. So I don't think that will be better, but we can try. So the numbers just keep changing. It's kind of interesting. It's probably some GPU clocking thing. Okay, so 3.62 milliseconds. So then essentially what you're saying is, what if we always run this code, but instead of hard coding this max distance, we add max t here, we pass it here, and then we say trans max t. So if we hit something, then it should be 0, otherwise it should be 1A3. And then we just always do this like this. And then we actually fix our code. Oh, like shadow hit or, I guess. I'm not sure if short circuiting, this is the same, right? 362. Yeah, so it's exactly the same performance. It's kind of sort of, I guess, maybe expected. I'm not sure. The way, there's no check for max t in the ray tracing implementation, but what will happen is the first thing that the ray tracing implementation will do is it will do a trace through the top level acceleration structure to see if it hit like anything at all. And the first node, there's going to be some bounding box. And so, but I guess we are starting the trace from inside. So I would expect that probably with max T0, we might do a couple iterations of the traversal loop in this code without this if, but it's not like our problems are so much more than a couple extra traversals, a couple extra like memory accesses and stuff like this. Like the work that we are doing here is so much greater that it probably doesn't really make that much of a difference. But yeah, it's an interesting suggestion. I think it's in general not a bad way to do this. If you can reduce the distance to make the ray hit fewer objects, that like might be a good idea. But yeah, in this case, it doesn't seem to matter. Okay. 73. Yeah, I changed from this code. The first time I've written this code, this was this, and then I've changed it to not none, which is the same thing. Am I doing, sorry, when I said the Roblox question, I didn't refer to the IBL question, I referred to the first child question. If I'm doing IBL for the specular occlusion in the shadow, it is. No. One thing I forgot to say, which I changed slightly, which is a dirty hack, is I added what's usually called shadow ambient term, which is, I hesitate, it's not IBL at all, but you can do IBL in a similar fashion. But like the way this, the way the scene looked last time technically is slightly different. I forgot to say this. So the way this scene looked like last time, my shader loading is broken. Oh, oops. All right, so the way the scene looked like last time is this, and I added a small term in the shadows so that in the shadows you see a little bit of a difference based on the normal. This is a hack. It's not super motivated physically. The more physically motivating thing would be to do IBL even on areas that are in shadow, and then have HDR and bright light source so that these things just add up, but then, you know, with reasonable exposure, you only see the effect in shadows. But yeah, I'm not doing any of this. The BRDF setup right now here is very, very simple and wrong in many cases. We will work on some of this hopefully at some point in the future. But once you start doing ray tracing, you need to start thinking about, you know, oh, like we are doing some sort of global illumination approximation. In the past, we would just hack this with some constant factor, but ideally, because you have a ray tracing option, you should think about how you get that from the real scene by casting a bunch of rays and denoising and whatnot. So BRDF explorations can go fairly far with ray tracing because there is so much more data in theory that you could fit into them. But I'm not doing any of that right now. It's just a constant factor. Okay. Wait. How are the call flags working? Yeah. There's two ways to specify the flags. One way to specify the flags is that when you build BLAS data, you can per geometry here. So when you build a BLAS, you pass it the geometry information structure, and it has geometry, and geometry has flags, and flags have an opaque bit. So this is one way how you can distinguish. Whatever's marked as opaque is opaque, whatever is not marked as opaque is not opaque. The other way to do this is that when you build a TLAS, and wherever this code is, Whenever you build a TLS, you say which blast I'm going to use, but then also you have these geometry instance flags. You can change the culling handling with them, but also you can say either force opaque, which means disregard whatever flags on the geometry, on any geometry in the blast that I'm referring to, and force the whole object to be opaque, or force the whole object to be not opaque. Both are useful in different circumstances. Both the per object and per geometry and per instance options are useful in different circumstances. For example, if you took the whole static scene and assembled one big blast from it, which we are not doing, but we could, then you really want an ability to have these different bits on the geometries. Because we right now have one geometry for blasts per blast, and then the actual scene is composed of these individual smaller meshes. For us, it's easier to specify these on the instance level. I thought this was supposed to, I guess because everything is not opaque. What the heck? Hold on. What, did I miss? Was there an opaque flag actually set here that I just missed? Oh yeah, never mind. Yeah. Right, so what we are doing is we are setting the geometry flag to opaque when blast construction happens, but then we are overriding this during the instance construction. Technically, this should be redundant in the sense that we could just remove this, and then in the TLAS, force either opaque or non-opaque bit. I think this should be the same. I don't see why the performance characteristics would be different. Yeah, 362. And then there's like a third way to do this, which is when you cast array query, you can actually override all of these flags. So you can say shadow comp. There's a flag called force opaque, not called just force opaque or something like this. It just says opaque, unfortunately. So the third way to do this is when you cast array, you say, oh, treat all of the intersections as opaque or non-opaque. Okay, so there's kind of three levels. You specify the flag per geometry, then you can override it per instance when in class, and then you can override everything per array in array queries. Wait, are we even using these? What is this? We are not using these variables anymore, right? Yeah, okay. I guess I'll keep, I thought I was not setting any flags per geometry, but I actually was, but I don't think it should matter. To be unspecified, this should not matter as long as class overrides them. But it's just cleaner. Having said this, I think the reason why I did this originally is just your baseline assumption is geometry is opaque, and then you can override this on the per object level to not be opaque, which is also fine. Either way is fine as far as I know. Okay, cool. So, all right, so then we are done with all of this. And then the issue that we have is that we have the code that we've written. So it's a little faster now that we are doing this two-way stuff, but it's still slower. So we can toggle it on and off, and it costs us almost a millisecond at 4K, right? So we go from 2.8 to 3.6. So this is not ideal. This means that we need to make things faster again. In general, I think this is a useful way to think about rendering in certain cases. In some cases, it's useful to just go for a final picture, for example, or whatever. But what I find, one way what I find that can work well is you have some sort of budget in mind. until you are below this budget, you can add quality by implementing more things. But once you're close to the budget, you have to trim fat, you have to optimize to gain back the budget for more effects. And so like we had sort of decent performance, so we've implemented more code to blur the shadows and all of this. But in the process, so if I disable both of these, this is how things used to work 2 streams ago. No shadow blurring, no transparent objects, just a single ray, very straightforward. At 4K, this is 4 milliseconds. We've implemented these 2 things. Now at 4K, we are 6 milliseconds, right? So we are 50% slower for the full scene rendering. We have nicer shadows now, clearly. So like, I mean, I like this picture less than I like this picture. So I'm happy with this, but this means that we should now work on performance to reduce the cost. So there's 2 ways to improve performance right now. I don't know what else I could do in shadow traces, because there is only 2 ways as far as I know to do this, either 2 rays or 1 ray where you handle everything as the ray is going. We tried both. One was faster on this driver. We picked it for now. That's kind of what it is. And then the actual mechanics of the ray tracing, as I was talking about last time, are very hidden in the driver. It's not like we have the freedom to organize things better. There is still things we could do. For example, as I was saying, can I still show this? Yeah, like, so if you look here, it's going to be a little hard to see, but this is the shadow from this decal. Like, decals cast shadows now. This is useless, and it probably is not free. Now, is it expensive? Probably not, but is it like, there's 2 ways to ask these questions. One is it costing us a lot that we have decals in our glasses casting shadow? Probably not a lot. Is it improving the ray tracing performance or decreasing the ray tracing performance, the fact that decals are in glass? I mean, it's probably reducing it. So ideally, we would remove these decals completely from our scene. The problem is, I don't think they are tagged at all in the scene. So like, we have a GLTF file that has a bunch of objects, and I don't think the vegetation here is mechanically different from these decals. I think they're the same. Maybe decals are one-sided and alpha tested, but that's like a really weird criteria to apply to filtering objects. I'm not entirely sure. So I'm not entirely sure if we can tell decals from non-decals. But so like, there's things like this that you can do to try to optimize traversal a little bit. And then you can also start doing level of detail, which I assume will probably not help much with performance, but it's a thing we might have to do at some point for correctness. For now, we don't need to really, but at some point we might. But that's kind of about it. And so then the only real other lever, I mean, I've tried the data rearrangement didn't help. Maybe there's a way to do it better, whatever. The only big lever that we have really is to do shadows in low resolution. Now, when your shadows are pixel perfect, doing them in low resolution will reduce quality. But when your shadows are already blurred, in theory, the quality reduction should be less severe. And I kind of get the feeling that with this GPU, with ray tracing in general, I feel like you fight for every ray that you cast per final resolution of your pixel. But especially with the AMD GPUs that have slower comparatively ray tracing capabilities, it just feels like you don't want to do, at 4K, right, again, high resolution, but still, you don't want to do this. And the other thing, I already mentioned this in the beginning, this is not even the worst case for our shadow tracing performance, because what I actually want to do, so let's see, 3.70, let me restart this so that we have a stable camera. So shadow trace cost 3.62 from this camera. I could just reload shaders. So as I already said, what I want actually is I want an ability to get the ray intersection distance from the raycast. But the only way to do this would be to get to switch the mode. You can get it right now, but the results are going to be wrong. So the correct way to do this is to switch the rays to remove this flag. But if I remove this flag, do I have to confirm actually? Hold on. No, this is fine. I think this is fine. Yeah, but if I remove this flag, things are going to be slower. So let's see how much slower. 5.17 from 3.62, right? So there's still a substantial, dramatic reduction in performance that awaits us if we remove this flag. It's maybe too much to even think about doing this. The only reason why I wanted to is, again, as I was saying, essentially, if in these pixels I knew that they are far away from the object that is casting shadow, and in this I knew that they were close, then I could change the blurring thresholds to blur more here and less here. There is another way to do this, I guess, which is you can estimate the variance, but that's probably just not going to be that good quality-wise. So this is the problem, right? Like, this is not even the worst case necessarily for the shadow cost, and shadow cost already feels like it's too high. So let's try and do this at half resolution and just see how it looks, and then, you know, maybe it's fine, and maybe it's not fine. So how do you trace rays at the half resolution? Because we have done this deferred setup and split the shadows and stuff like this, I talked about this last stream, this shouldn't be that bad. What this requires us to do is to have a lower resolution version of our depth buffer, except that I don't even need this necessarily. So what I will do, I think I can just keep, can I just keep the code? Like, I need some tweaks. But I almost feel like I can almost just do that otherwise. Oh, and this will also accelerate the blurring cost. There is other ways to accelerate the blurring cost. But, and technically you could cast rays at half resolution but blur them at full resolution, but that feels like completely useless. So, yeah, so I think it should be actually very easy, hopefully fairly easy, to try this, but then we'll have quality issues and then we'll try to fix them and then we'll see what happens. I'm debating if I need a half resolution image for the depth or not. Let's just do a very dumb thing and then see what happens. So the very dumb thing is very, very stupid and straightforward. You just like allocate a smaller shadow map, shadow buffer. If either of these is 1, then the texture will fail to be created. Let's ignore this. Very valid concern for now. And then is this like it? There's 2 more things that you need to do, but I feel like the code will actually even just work if I don't do them. Well, no, when I blur, okay, so I need to do more changes, of course. In the interest of keeping this code slightly more generic, let's do like shadow resolution or something like this. Or shadow like downsample. So we need smaller shadow targets. And then the one thing is when we blur with compute. Oh, and I guess when we cast rays as well, right? Yeah. we need to divide the resolution. So here, shadow downsample here. Oh, and these are different as well. Do I have dimensions in the image objects? So like shadow, blur, target? No. Okay. Unfortunate. So then, yeah, I have to change these everywhere here, if that's the case. Is this a stupid warning? Yes, this is a stupid warning. Okay, I don't know, let's just run it and see what happens. This is not correct code, to be clear. Okay, it's not too bad. It's gonna be bad up close, I'm sure. Even up close, it's not too bad. But there is issues, yeah. Okay, cool. Okay, so this is encouraging actually, because the issues that I see, they are minor and I know how to fix them. Let's talk about what happened. Because yeah, so like if you disable blurring completely, then you see that the shadow, I'm not sure if you can see this on the video feed, but shadow is like slightly half resolution. But practically speaking, you want some amount of blurring, I feel like, regardless. Like I don't think you want this, I think you want this. So that's actually completely fine. Okay, all right, okay. Now there are some issues. So this I'm more worried about actually. Yeah. Unfortunately, there is not a great way for me to be able to toggle this on and off. I mean, I can write code to recreate the targets and stuff like this. Should I do this? I don't want to spend time on this. I can, I guess, shelve. What's the best way for me to do this? Let's try this. I haven't tried this before, but it might be interesting. It might work. Like, I don't see why it wouldn't work. Okay, so we will wait, what? Why does it not work? Interesting. Huh. I thought they added splitting support, but I guess it's broken. Alright, so I will have two terminal windows. And then in one of them, I will run the full resolution version. Oh, dash. Oh, I should have switched to release. It's fine. And then in another one, I will build and run the half resolution version. And then we will look at the differences. There is one difference that I'm not worried about because I know how to fix it. And there is one that was a problem before that I am, because I'm not sure what to do about it. Oh. Oh, this was a problem before? And it did not get worse. Okay, maybe I'm fine. So the thing that I don't love about this is that I don't know if you can see, but if I move the camera, there is significant shadow aliasing under this table. If I'm close, then this looks perfectly great and normal. But if I'm far away, then it's bad. And there's sort of a reason why it's bad. It's kind of just like an aliasing problem. And I was worried that it got worse with the half resolution, but actually I don't think it did. I think it's about the same. Okay, so let's try to compare these side by side. The camera viewpoints are not quite the same. And then like look at the differences. So there's two things. So we are now, the left image is the previous one, and then the right one is rendering things at half resolution when we built the shadow map. But then the actual image is still rendered in full resolution, of course. And then if we look at the timings, this might be slightly weird because there's two apps running side by side. But you can see here it's like 1.5 millisecond shadow trace versus 0.4, right? So clearly there's substantial performance improvements to be gained here. And oh yeah, this is the problem. So on the first glance, things look okay. Like if I don't move the camera, if you just look at these static images, both look okay to me. If I zoom into this thing, then this kind of looks okay, but it looks different. The left image is less blurred than the right image. This is the exacerbation of the problem that I was talking about, where I said, hey, ideally I would not blur an image at all when I don't need to, like in the regions that I don't need to. And so this is hitting this problem kind of more severely. But the reason why this happens is we kept the blur code running at the same resolution that the shadow map was at, with the same kernel size in pixels, but the pixels are now larger. And so now the blur is across a larger distance. So in principle, we can fix this by reducing the blur kernel width. The blur will run even faster. We could try to do this, I suppose. But then it runs into some noise reduction issues. So that's like the first problem, right? The blur is different now. The second problem is, let me see if I can show it here. Yeah, so if you look carefully along this edge, and then along, I guess, the same edge from similar camera here, you can see that this looks perfectly normal, but here there's like a white outline. And the reason is the shadow is being rendered at a lower resolution here, but then it's being reprojected, sort of like the results of the shadow cast are being used in the high resolution. And so in some of these pixels, you're going to pick the pixel that is not in shadow. And so if you pick on the left side of this wooden thing, a wooden plank, the pixels are in shadow. On the right one, they are in shadow. And so if the pixel from the wrong side picks like the shadow pixel that was computed for the wrong side, then you're going to have bad time, right? But this is kind of a problem that we already had to deal with last time when we talked about blurring and bilateral and depth aware and stuff like this. And so in the same way how you can do bilateral blur, you can also do bilateral upsample, where instead of using one pixel, instead of reading one pixel from the shadow map, you read more than one, and then you either pick the one with the smallest depth difference, or maybe you blur them, or like you average them with the weights based on the depth differences and stuff like this. So this is like a solvable problem. There's the third issue, which worries me, which we had last time, but it's now more pronounced. I don't know to what extent you can see that. So if it's also kind of shadow aliasing, but I think it's because of how the blur is being done, how the jitter is being done. If you look at this region, if I move the camera back and forth, right, there's like, it's sort of shimmering that's going on. And here it's the same thing, but it happens sooner. Like this is the distance that it happens at, whereas here at this distance, this looks completely stable. It feels like this should be fixable. Maybe if I adjust the blur, but I'm not sure. Let's try to keep running in this weird split mode because I can reload the shaders into the right copy, which is the recent copy. And let's see what happens if I drop this slightly down, not quite 2x, but almost 2x. Yeah. Yeah, so the blur implications are unclear to me right now. There's nothing fundamental about the drop in shadow resolution that should create these artifacts specifically, as far as I know, because this portion doesn't have like depth differences and stuff like this. So like this is a fundamental problem, which you have to fix. This, I think it's not, but because we have to retune all of the blurring somehow, I'm not sure how this will interact. Let's do this. Let's do this. I think this is the right direction for us to go. And again, I know how to fix this problem, but this problem I need to think about. And it's already been 2.5 hours. So let's do this. We will do half resolution at some point in the future. This diff is very, very tiny, right? Just to give you guys a sense again as to what it would take to fix these single pixel artifacts, it should be fairly straightforward. In the shader where we sample the shadow map, where we just sample 1 pixel, this would have to fetch 4 pixels. I would need to think, there's a couple different ways to do this. You could fetch left, right, top, bottom, and stuff like this. You could do gather 4, but then you have to offset things a little bit, maybe for things to line up. So there's a couple subtle ways to deal with this. But fundamentally, essentially here, we'll have to, like, let's say we had also shadow 1, shadow 2, shadow 3 for 3 other pixels in our neighborhood. And then we could also sample depth for these pixels as well. And then similarly to the blurring code that we had here, where we took the depth difference and then fudged some math based on that, we would either select one of these 4 values based on the delta, or we would blend all of this based on the delta. And this should generally work decently well. There are some really weird cases where it might not. And yeah, like it should fix all of these artifacts. There are some cases where this might not be a great idea. But the blur thing, which you see even here, worries me more. And until I'm confident I can fix the blur thing, I don't want to drop the shadow resolution, because we would go from a picture that looks pretty good to this mess, which doesn't look as good. So, because of this, and because I don't feel like I want to explore all of this fully, we are going to do a very quick thing that hopefully will get us a little bit of performance back in a different way. And then, you know, that's going to be the stream. And then I'll think about, I'm not even sure if there's going to be a stream next week, because I have plans for the holiday week, but this is the weekend before this. We'll see. I'm not sure when the next stream is going to be. Not guaranteed that it's going to be next time. But yeah, instead of dropping resolution, let's just try to quickly slightly optimize the shadow blur in the way that I was talking about last time, just to see if this is possible, if this will help, etc. And then we'll just call it a day. The shadow blur is a nice optimization target because it's a more fixed cost thing. It just costs 1.03 milliseconds at 4K. There's like not, it's always the same. And the thing I was talking about last time that I just want to quickly try is when we do shadow blurring, because of the fact that we do bilateral blur, we have to have access both to the shadow value and to the depth value of every pixel. And to get that, we do 2 samples per pixel, and then we do 21 samples in every pass, and then we have 2 passes. So we have twice as many texture samples roughly as we could do, or we have even more if we were to explore using gather and stuff. Do I feel like doing gather? So there's 2 ways to solve problems like this. One is you merge both of these values into one texture. The problem with doing this naively is the depth is the 32-bit value. It needs a lot of precision and stuff like this. But there's probably, because we don't need the precise value of depth, there's probably a way to pack this somehow for it to not be that slow. The other way to deal with this stuff is to use this thing called textureGather. Because the other insight, and you can do stuff like this in traditional sort of blurs without the bilateral component as well. We are also fetching 1 pixel from the texture at a point in time. But the thing that the hardware actually likes to do is to fetch a 2x2 footprint of pixels at a time, because this is how texture filtering works, right? Bilinear filtering works by having a 2x2 texture fetch from the texture, and then you blend between the 4 values, and that's the final result. So there's a way to access the individual values from a texture using this textureGather instruction. And notice this gives you 4. So the other way to optimize this blur, maybe this is actually better. So the other way to optimize this blur is to do gather on both images. Gather returns you 4 values. And then there's a question as to why this is helpful. So the first thing you can do is you can reduce the number of iterations, because you can blur like 2 pixels at like in a horizontal direction. If you're blurring in that direction, instead of doing 10 steps and aggregating 1 extra pixel at every step, you could do 5 steps and aggregate 2. That only uses 2 values out of 4 that you get for free. And so the second thing you can do is you can process 2 values at a time. And so essentially you have 2 things that you do here at once, and then inside the loop iteration you do 2 things at once instead of 1, and that gives you the full utilization of the 4 values that you have fetched. And that's in theory much faster. So that's kind of the 2 possibilities. The one requires aggregating more data into the texture, and then the other one requires using gather. They are sort of compatible, but sort of not super compatible. Because gather is usually used on a single component texture, you can use it on a 2-channel texture, but it's, I guess, probably just less beneficial at this point. Because I kind of want to do the simpler thing without gather, because I kind of feel like I will need more data to do shadow filtering anyway, because of this blur radius thing. So I kind of feel like I need to do that upgrade in the future. And so maybe I just want to do it now. Let's see if this regresses. This requires more data in every pixel. Because of the depth precision issues, I kind of want to switch to 16-bit. So let me first see if just bumping the formats to 2-channel formats makes the performance of this shadow filtering worse at all. Because it might. It did a little bit. So it's now at 1.07. But this is a substantial increase though. So, okay, let's try to work with that for a little bit. because maybe that's still a good idea. But I hope this makes sense. And I kind of don't want to do gather right now because I'm not sure. I'm honestly just tired, so I don't want to do it right now. But maybe we'll do this in the future. So okay, 0.52 milliseconds for this half resolution shadow blur, but with the wider texture that we have added, I think it probably would have been 0.49 or something before. Let's just see if we can quickly hack in this depth stuff. So the value that I want to save in the texture. This is where things like this get tricky, because you have to think about precision and stuff. So it probably was a bad idea to even embark on this journey right now, because it will take time, but okay. Just very, very quickly. So what would happen if I had depth factor, which is, let's say 1 over, do I have depth here? Yeah, 1 over depth. 1 over depth is not quite correct, but it's kind of almost a linear approximation that the value is clamped, so if it's too close to the camera, it'll get clamped in a bad way. And I don't know if 16-bit is going to be enough precision is the issue, but let's try to go. I should actually use value more closely related to the near here. But let me just quickly try to hack this in, and then we will see. Because now essentially what should happen, and there's 2 passes, and so in the second pass, I want to preserve. So if we are not doing blurring, none of this is useful. If we are doing blurring, so we're going to preserve it when we do the blur. And then when we sample from the shadow image, what we could do instead is keep 2 channels, in which case the first channel is going to be the actual shadow value that we have had so far. But then the second thing that we do, and this is where I don't know if I'm going to lose precision doing that, is that I can just take this value from the sample that I've already done. And this does nothing to the shadow performance. Today is the day of failed optimizations. Oh no, my shader doesn't compile. Okay, cool. Yeah, okay, fine. Let's keep the original name. All right. So then, obviously, this is broken. So let's see. Oh yeah, I have to rescale it. This super doesn't work. Hold on. Yeah, the value is between 0 and 1. One very lazy thing to do would be to just dump the value, the depth that we have into this texture, but I'm very sure that it's gonna run into issues with precision. But actually then what we want is, we don't want that near over depth, we want some maximum useful value. Wait. This is, I shouldn't have even started this probably. So this is linear depth, roughly speaking, but then the value is between 0 and 1. Okay, so let's just say we only care about like 300 units until the camera or whatever. And then we will keep this as is, we will keep the 300 there, and then here we will say, well, instead of this, it's shadows G times 300. Okay. Okay. So shadows blur is 0.28 millisecond with this change, and then 0.52 without this change. Oops. So this about halves halves the cost of doing the shadow blur. Now the issue is I might see bugs that I didn't have before because of the limited precision. But also I might see bugs because of poor tuning of stuff. So this is actually interesting. So, okay, hold on. Let me just add a variable for this. And then we will... And then we'll just toggle between this and see what happens. The results do not change at all. The bilateral stuff requires more tuning clearly because, and this is kind of, I reverted the change before the stream started because I wanted to tune it a little bit more, but I didn't quite do it right. So maybe this is not too bad actually. So what I'm expecting though is I'm expecting some amount of precision issues somewhere because I'm using like a 16-bit component to represent maybe this is even fine actually. So let's do this again. I don't see any changes in any pixels. But yeah, this is an artifact from last time that this change doesn't make it better or worse. There's like better ways that I was playing with that went something like this. What about now? But then these ways, I think we're creating weird artifacts here, or maybe not. Maybe I should have actually just done this change. Hold on. The issue is, let me talk about this briefly. Yeah, it does change. Let me switch to, I don't have like a hotkey for this, which I probably should add. But when you debug shadow issues, you probably should debug shadow issues, not like other issues that you might have. Okay, so this is the actual shadow map or shadow thing, shadow trace buffer. After the blurring. So it doesn't change at all when I toggle this depth packing thing. And then what I was playing with, this is actually just fine. The issue basically with this part, yeah, I guess the shadow view makes things easier to see, so there's probably some more issues here. Well, so the shadows without the blur look kind of like this, and then the shadows with the blur look kind of like this. But so what I had here before, this is from last stream, is that when I did bilateral filtering. The problem is the bugs. I'm just being very confused right now. Hold on. I should have some mode here that says, do the shaders have a bug in them? Interesting. So this view, it seems like it should be easier to spot shadow bugs on the view that only shows shadows, but actually on this view it's very clear that we have a bug in our bilateral filter, and in this view it's extremely unclear because, like, who knows, there's an edge of an object. Is it off by pixel? Is it not off by pixel? Okay, so this problem, right? When I added bilateral filtering on the last stream, I just said, let's take the delta between two depth values, and then based on how far they are from each other, let's scale things. The problem here is, and depth in this case is the linear depth, meaning it's the distance from the camera plane to the pixel in world space units. There's the linear thing, which is making it differently. I guess this is the tuning that was here last time. So that's kind of the same though. So this factor shouldn't really affect anything because it's just like multiplicative. It will affect things a little bit. Anyway, the problem with this formula though is that in this case, the depths of all pixels that we are seeing in such an extreme close-ups, they are of course very close to each other, right? So the depth here and the depth here are of course very close. If we zoom further away, then the distances between these pixels are of course the same, right? But the distances between pixels here are different, right? So the issue is this value is a little bit hard to tune if you use an absolute scale, because okay, so clearly we can still blur pixels that are too close in depth together. So this means to fix that we should increase like this blurring factor. So let's say we increase it to 200. Even 200 is not quite enough. I don't even know what it should be to completely hide this artifact, but let's say 1000 is close enough. There's still some issues here, so it still doesn't fully fix it, but it's closer. Okay. The problem though is if you have an angle like this, for example, then you will see that the blur here, I think it looked like substantially different. So if you drop this factor back to 20, is it true? Maybe this is not true. So I guess what I'm trying to say is just that there's differences in tuning, different ways to tune this value, and sometimes you want it to be relative to the depth, maybe, but sometimes maybe an absolute value is fine, but I'm not even sure I'm right anymore, because I was playing with a relative delta before the stream, but maybe, yeah, so on this actually it's pretty clear, it's pretty interesting. What you want to have here is you want to have no bilateral effect at all on the blur, because the difference between depths of these, while the depths are different, the pixels are like on the same plane, so like they should all be blurred together. But this doesn't quite work if we increase the factor. So like if we increase it more and more, you can see the blurring is effectively disabled here. But we want a high factor to fix problems here. So then I thought, okay, maybe if I do like a relative thing, then I can have a better balance between these two factors that kind of compromise each other, because I can have the reasonable blur here, but then also not see these artifacts to this extent here. So maybe, I don't know if there's a right way to do bilateral blurs or a wrong way, as I was saying last time. sort of just there is a balance to what extent you want to separate the objects that are kind of that have different depths, and what does this mean? Like, do two small bumps on one object, should they be blurred together or not? What is even an object? So there's not like a right way to do this necessarily, but maybe I should keep the relative thing, because the relative thing seems to work reasonably well. And none of these concerns anyway affect our optimization, because it doesn't, the behavior with it is exactly the same. It's just that the code gets like twice as fast. Okay, so let's just assume we are doing this optimization. And there's this 300 factor that I'm not proud of, that ideally should be extracted somewhere, but I don't have a place to store the constants. So I guess I'll just keep it here for now. I guess I'll just keep it here for now, whatever. So in full screen, what does this net us? In full screen, we started from 1.03 on the blur, and now we are 0.6 milliseconds on the blur. So it makes the blur not quite twice as fast, but close to twice as fast. Gather could have been a little better maybe. So maybe gather will be better to do in the future as well. All right, I think this is good enough. It's actually a 3-hour mark. So I think this is just, yeah, I don't feel like dragging this for too much longer. I will probably commit this change. This is easy to undo in the future. We might want to rework this, but it's a neat way to do optimizations on some filters that isn't too costly. Now, it did cost us a bunch of memory, so we are paying a 4x memory cost right now for a 0.5 milliseconds of frame time. And whether that benefit is worth it, I don't know. Gather could have been better. You know what? Whatever. Let me just. The full gather is more difficult to try in earnest, in some sense, but I think it's easy enough maybe to try very quickly. So let me just stash this. I will not commit this for now. Maybe I will look at this off stream later, and then if I commit this code, we technically route it on stream, so it's fine. But I am just curious. I should be able to hack a 2-wide gather very quickly. 4-wide is more painful because you have to change the dispatches. You have to worry about what if your swap chain is like of odd size or even size or something like this. So, but if 2x gather is as fast as what we have just done, then even a 2x gather is worth doing. So maybe that's what I should try. Okay. So then again, the idea behind the gather optimization is like this. Instead of using texture, use textureGather. You give it the position where you want to sample. You give it the component that you want to sample from, but by default, it's the first component. It gives you the 4 results. And the 4 results, it doesn't say here, well, it sort of does. They're structured like this. It's like the oh, because it's the OpenGL documentation, I guess, it uses the stupid OpenGL indexing mode. So it should be like indices in scan order or pixels in scan order, meaning X component is the left top corner of the 2x2 rectangle, and the second one is the right topmost, and then there's the 2 bottom ones. When you do this, there's a question of how you pick the 4 components to sample. And the answer is it's the same way that Berliner or nearest filtering picks them, kind of. But for this to work reliably, you have to sample not at the center of the pixels. You have to sample like in between 2 pixels or 4 pixels. So for us, what this means is that we need to move the sample offset. And then we'll have to do this for 2. Okay, so then the theory goes like this. Let's just duplicate the body of this loop. Make it loop 10 times less times, 10 times fewer times. And then for every kind of iteration of this loop, we are going to unroll this very mechanically. So just unrolling the loop 2 times. This is not necessary for performance because the driver already does this, but this is going to make it more obvious as to what the gather thing is going to do for us. So so the problem is it's not I times 2 plus 1, because from -5 oh, and the middle sample you only want to do once. Okay, this is actually painful. Hold on. So you have to split the loop, right? Because we are doing 21 samples, and so if we do 2 kind of samples per iteration, then we can't. Why do we even have? So I think the correct thing to do here is essentially, okay, so if I equals 0, we should just skip the iteration, and then we should start shadow from the shadow sample. This is UV times R, and then the weight should be 1 presumably, because all of these factors should be 1. Okay, so hold on. So this is just, I guess, good to do. This shouldn't change anything at all. Oh, actually, I think it makes things a little faster. That makes sense. So we were. Oh, I am not reloading. Never mind. All good. Okay. Okay. And then if I go all the way back. Yeah. Okay. So this is exactly this the same. It runs at the exact same performance, but now we sort of have 10 taps that we do in one direction and then 10 taps that we do in another direction. So now we should be able to unroll this into. So we do this. We do this. You know, I had a perfect opportunity for this to be a 2-hour and change stream, and instead it's still going to be a 3-hour and change stream. Why do I do this to myself? So I1 is I times 2 plus 1. And then whenever we use I in the first iteration, we will use I0. In the second, we'll use I1. Okay. So this should be exactly the same again. No performance change, no nothing. The reason why I did this like this is that now it's more obvious that these texture samples are almost at the same offset. One is just slightly off from each other. So what we could do is we could do off between them. And it's essentially I0, I1 over 2. There's like a cleaner way to compute this because this is I times 2 plus I times 2 plus 1, which is I times 4 plus 2. And then you divide it by 2. And then you get I times 2. What? Wait. That can't possibly be right. Hold on. Interesting. I guess this is just how the math works. It's funny. But I'll keep it like this. I'm sure the compiler will simplify this. And then what we can do now is we can do gather of both the depth image and the texture image. And gather returns you 4 results, but 2 of them are going to be basically useless to us. So we will only use 2. And then we will do the same thing for shadow image. And then in theory, this should be the same fetches that we are doing here. It's just that we did 2 texture operations to do 4 texture fetches. And so in theory, we can now do dgr, dgg, and then dsr, dsg. And our blur is heroically running at the exact same cost, but that's because our code is not compiling. dg and wait, what? Hold on. Oh, sorry. Wait, instead of ds, I called it sg, ShadowGather. Okay. Okay, this is actually also doubling the performance basically, but with no memory consumption. I think the results should be exactly the same. Let's try to flip back and forth and see if that's true on some weird, like, let's try to flip it actually on a region like this that has these filtering bugs. So this is what it was before. This is 0.47 milliseconds, and then this is the result. And then the result did not change at all. Okay, this is way better. So this is the same performance gain, which kind of makes sense because we were doing 2x fewer texture fetches there as well. But here, the way that we are doing 2x fewer fetches is by doing the textureGather and then reusing the results that we had, because we need to process more than like more than 1 pixel, I guess. Like as long as you are fetching your pixels in groups of 2, you can use a gather to reduce the number of fetches by 2. And again, what we also have right now is for free, we are actually gaining access to the gather for the second row of pixels, which we are just completely discarding. It doesn't affect our performance at all. But this means that in theory, we can improve performance even further here by doing 2 rows of the image at once. Okay, so then that's actually good. That's much better than the thing I had. Let me try to streamline this code then, because there is duplicate heuristics that should be doing the same thing, obviously. So then essentially what you want is you want all of these values to just come in pairs. So instead of a float, the Gaussian weight is a pair, because you have them for sort of, let's just do IP vec2 I0 I1. And then, so all of this math can be vectorized. This by itself does nothing to the performance, because the GPU scalarizes everything anyway. But this just makes it easier for us to write vector code, quote unquote. So then, I mean, from here on, we might as well just do this. The only reason why I wanted the only reason why I wanted here the computations to be on one line is just because these are weird computations that fudge a bunch of factors together, and so they should be the same, of course, between 2 variants. Okay, let's see. Okay, shadow blur is 0.56. This is actually slightly better than our previous attempt with the single texture. Okay, so gathers actually were a better idea, and we have this free opportunity to make things probably twice as fast again. I'm not sure. to do that, we have to double things up. We have to process two output pixels at once. So all of these become sort of float two vectors. And then this loop starts dealing in 4 vector quantities, and then it keeps 2 vector 2 accumulators and stuff like this. I don't want to do it now. It's a mechanical transformation that will get us an extra 0.2 milliseconds, give or take. But it's going to be potentially valuable to do in the future. I just don't want to do it now. Maybe I'll do it off stream, but I hope you kind of get the idea. Gather gives us 4 pixels, and we have 1 pixel we are processing, we are generating now, but because we can pair up the tabs that we do in the kernel in groups of 2, we can use half of the gather capacity, and we can use the other half if we do sort of 2 output pixels at once. Gather only returns you a 2 by 2 group of pixels, so it can only do A, B, C, D if that's the texture layout. It cannot do A, B, E, F, so it can't do 4 pixels that are sequential in the texture. It has to be a 2 by 2 group. Okay, that's actually cool. That's a more generally applicable trick. I am happy that it worked as well as the other one. And this means we use less memory because we don't need to like increase the shadow texture at all. And also this removes the concerns about depth, precision, and whatnot, because like this is just the original depth values. There's just 4 of them that the texture hardware fetches for us at once. Okay, cool. So I think this is where I want to end. This is a good, neat, small optimization. Of course, the real thing is reducing the number of rays that we cast. And to do that, we need to reduce the shadow resolution. And to do that, we need to deal with noise concerns and quality and all of that. And I don't feel equipped to do this right now. So, and I'm kind of relying on the driver to unroll this loop. It might not. It doesn't have to, technically. But I kind of hope it does, because this branch, I guess even if it doesn't, this branch is fine. It's perfectly predictable. It's perfectly coherent, etc. It's fine. But I looked at this in the past, and at least RAD driver fully unrolls this loop at 20 taps. And now this loop is actually smaller because it has fewer gather instructions in it, fewer texture instructions in it. And so hopefully it will unroll it even, even more readily. But yeah, that's kind of, I guess we can do like final weight. Okay. And then I'll probably do a 2-to-1 transform off stream. The only thing that has to happen there is dealing with swaption sizes that are not even, and that's painful. I don't actually even know how the unaligned swaption sizes work, because I'm like nonchalantly using image stores and stuff, and image store doesn't work, I think, in Vulkan if the position is out of range. But I don't actually have any guards here. So actually like an extra 2x optimization here should be straightforward to get, but whatever. I feel like I've explained the extra 2x optimization in sufficient detail. So I'll just finish this code off stream, and that's gonna be fine. Okay. All right, people, that is it. I'm tired. It's been a while. Let's see. Let's go through questions, and then that's where we will end. How hard is it to make shadows be really sharp at the intersection, be more blurry the more far away the shadows from the object? So yeah, this is not hard conceptually now, because the only thing that needs to happen is we need to record the intersection distance and then compute the width, the kernel width, based on this intersection distance. And then that will it fight the gather? Nah, the gather is going to be fine. I don't want to do this right now, but let me just briefly show what is cheap to get. Well, sorry, what is easy but expensive to get. So I've disabled shadow blurring, so the value is now just the shadow, right? And then let me also disable, how do I do this? Actually, yeah, so let's do this. So then instead of a boolean, I will return a float. There's gonna be like negative if the ray didn't hit anything, and then it's, or my rays don't even start at 0. It's gonna be 0 if the ray didn't hit anything. So if the ray is, if the ray hit nothing, we're gonna return 0. Otherwise, what you can get from the ray is, oh my god, sorry, array query get hey, where is this? What? Tmin is not that, right? Hold on, I need to consult this. Oh, yeah, it's spelled in a really weird way. It's it reads as array query get intersection text, but actually is get array query get intersection t, and then x is just, you know, a thing at the end. Okay, so instead of the Boolean result, we are going to return the intersection distance, and then we'll just assume that 0 means intersect nothing. Ideally, maybe you return -1 here. It's fine. Who cares? All right, let's just return -1 to not run into weird dishes before. So then the way we use this is we just say, okay, like shadow hit something if it's greater or equal to 0, greater or equal to 0. Okay, so that's like the same code. Nothing changed. The performance should be the same. I'm not sure if shade reloading works. Oh, this is my old. Okay, hold on. This is my old. 1 second. I actually need to rerun this. Maybe. Oh, it's funny. Like we were using shade reloading in the binary build from like who knows when. Okay, shade reloading is cool. So this is the same code. It should run at the same performance. Wait, did I break? No. Okay, all good. So instead of the 0 to 1 value that says whether, oh my god, whether we hit an object, what I'm gonna save to the shadow buffer, and I'm gonna disable blurring. What I'm gonna save to the shadow buffer is the actual distance. So I'll just kill this code, who cares? We'll just get shadow hit. And then if shadow hit is less than 0, we're gonna save 0. Otherwise, we are gonna save, let's just save shadow hit. This is fine. All right, now I have errors in my shader. Oh, I renamed it. Of course I have errors. Shadow dist. Okay. I guess let's do it. Let's invert it. Okay. So this looks kind of nonsensical, but sort of sensible. Let me just scale this by 2. Scale by 2. Okay. So you can see that I have, by just changing a little bit of code, I'm now outputting the value that is almost like it lerps, it's different close to the hit, right? It's not whatever the 0 is and 1 is here, I already don't know, but it's like next to the contact, it's, let's say, the distance is 0, but then we convert it to a value that's 1. Now you can use this value, if you propagate it through the blurring pipeline, to just determine the shadow blur size. Here's the problem. Look at this and ask yourself, what the heck is this, right? Like, this makes 0 sense. Okay. This is the query flags that I was talking about, that right now the ray is set to terminate at any point, which means that when we are tracing a ray through this object, we could get a hit on the front wall, we could get a hit on the back wall. If this object was in shadow, if this pixel was in shadow of something really far away, we could get a hit anywhere. Let's see if we have some egregious examples of just like weird stuff happening. So here things are mostly okay, but you see the weirdness here as well. Sometimes it can be really wild. I don't like if there is an object in deep shadow. So this, I guess, is a good example, right? This pixel is in deep shadow of the building. Well, on this one it wouldn't matter, because it is the closest. Oh, interesting. No, that doesn't matter. Okay, yeah, I guess even here you see this weird, like, things, right? So, like, this value doesn't quite make sense. So now, if I disable the terminate on first hit flag, magically, this value is now clean, right? This is the distance to the occluder. It's correct as far as I can tell. If you look at this thing, there's no like weird gaps here, etc. The problem is, and I was talking about this at the beginning of the stream, it's very costly. So right now shadows cost 4.5 whatever milliseconds, and then if I restore the original flags, they cost 3 milliseconds. That's like a crazy increase in cost, right? So it's like the value is sort of free for you to just get, but the problem is that the fast tracing configuration returns you the wrong result, and the slow tracing configuration returns the right result, but it's slow. So that's unfortunate, right? So like obviously if you blur the shadow of this bike using this value, you would get bad behavior, but this you would get reasonable behavior. Even this, I'm not sure. Even here I have some questions, but maybe that's fine. Maybe this is kind of how the bike looks from under it. Maybe there's some extra weird geometry here. Yeah, so this is the problem, right? The problem is it's easy to blur adaptively if you had this value, and it's easy to get this value, but it's really, really expensive to get this value. So I have undecided as to what, if anything, I'm going to do about this because of this problem. Like, I don't think it makes sense to pay 50% of performance for shadow rays for having access to this. But maybe that's the only option. So that's the problem. Some of the decals seem to be alpha blended instead of alpha tested. Yeah, I think I looked at that. And let me revert. So I thought I looked at this, but maybe I didn't. Because I feel like the decals were blended. Oh, maybe decals were blended, but vegetation was tested. Oh, that would be interesting. So I have this thing now that I can use I look at the parameters of the object and then I classify this somewhere. So right now I classify things that are not opaque as non-opaque. You could indeed do what you were suggesting and have different handling for mask versus blend. Oh my god, come on. So I feel like maybe this could even work. So this will hide, post pass 2 is like the thing that will hide. It will hide the object from the scene, but I don't have this fully fleshed out. This will hide the blended objects completely from the rendered result. I think they will still cast shadows, which is kind of weird. But okay, let's see what this does. So the decals are gone, but the vegetation is here. Yeah. So thank you. This is a good suggestion. So I think what I should do then, yeah, this is the decals. So it's still in the ray tracing scene, but that's because my filtering is wrong. Okay. Thank you. This was good. I will adjust the code probably off stream because it's like it's too easy to just remove the blended objects from the ray trace geometry. I don't expect this to be a huge thing from the performance perspective, but I mean, it's good to do this if you can. I forgot why I even did this way. Oh, this is to remove, this is because I don't actually have blended objects in the sense that the decals are just rendered with an alpha test. So I could actually do that maybe, and then disregard the transparency. This might be an interesting thing to play with. Yeah, I'll do that. Okay, so we already looked at shadow only render, so that's probably was from a while ago. The memory increase could be mitigated by half res. Yeah, it looks like Gather basically works pretty well. So I don't think that super makes I don't think it makes a ton of sense necessarily to do the channel the texture packing thing. But I'm actually happy that I had to revert to the texture packing and do the Gather, because both techniques are useful in practice. In the specific thing, what we saw was that the performance gain was sort of similar, and then maybe with Gather you can push things further. But then there's cases where Gather is just not an option, and packing more channels in texture is. The only reason why the texture became 4 times bigger is because I need 8 bits for shadow, and I couldn't use 8 bits for depth, because that would just be bad for performance, like very bad. But there's cases where this is not true, right? So there's multiple different ways to do all of this, but both of these techniques are independently useful in some cases. Well, dependently, you can't really apply both. Applying both wouldn't make a ton of sense because Gather only works with one component, but both techniques can be useful in different scenarios. Okay, I think this is a good place to end the stream. I will look at the Gather thing later. The biggest 2 issues that remain with shadows, the biggest 3 issues that remain with shadows. So one is this contact filtering thing, a contact distance thing that I just talked about. And it's like so easy to do now, but it's so expensive. And so I don't know what to do about this. And then the second one is the performance. If we do half res, my plan was to do half res and then I would just be able to afford 50% drop in the performance due to the contact stuff. So maybe that's correct. And then the last thing is the blurring. The noise artifacts with blurring, which in some cases things look really, really well. Things work really, really well. Don't look too close at that, but like here things are very nice. And if you look at this from a distance things look very nice. If you look at this from up close, you see this ugly stair stepping. So that's not cool. And there is some angles on some shadows where, yeah, like this, where you just go back and forth. Oh, there was some crazy. Oh yeah, okay, I found it. So, right. So this is like bad, right? Clearly, this only happens when the jitter in the ray substantially offsets the results. So this only happens when the object that you're casting shadows from is like far away. And it only happens on some specific alignments of the object. Like you have to find the right spot. But you know, this is the right spot and this looks completely terrible. This is like unacceptable, right? So that sucks. And the problem is you have to go way further into advanced noise techniques, I think, to actually like clean this stuff up. So we will see. Anyway, so that is it for today. Not sure when the next stream is gonna be. Might not be next week. We will see. I will keep you guys posted. Thank you for joining, and have a good rest of your weekend.